Now we're going to talk about the medical applications of radioactivity. Radioisotopes that we use for medicine, we specifically use ones that have short half-lives. So anything from a few days and under, like hours, minutes. It could even be about a month or so. But when it comes to start talking about years, we don't use things that keeps for years because we don't want it in our bodies for that long. They have the same chemistry as everything else in our body as the non-radioactive atoms. However, as they break down, you're able to see the energy that's given off. In the organs of the body, they give off the radiation that exposes on a photographic plate, giving an image of an organ. So we can actually see what the organ looks like and see how things are being absorbed. Here's some examples of the radioisotopes. Notice once again, we're talking days, minutes, hours. Nothing is in years here. After a radioisotope is ingested by the patient, it could be something that was in an IV, it could be something that was consumed like by drinking it or whatever. The radiologist determines the level and location of the radioactivity. And because of that, it gets absorbed into the body. For instance, if you have iodine, the iodine starts to get absorbed in the thyroid. And then we can put a scanner on top of it that moves really slowly over that organ that we're concerned about. And we can have a visual of what's going on with that organ. The gamma rays emitted from the radioisotope can be exposed, giving a scan of the organ. So here's an example of a thyroid. Here's a thyroid right here in the human body. The scanner's hovering over it, and you can see that there's a shape made. And that's all the iodine that was absorbed by the thyroid. With thyroid specifically, it could be not only looking at the shape, but also the speed of the absorption. PETs, positron emission tomography, is things that have an even shorter half-life. And we use these to study brain function, metabolism, blood flow. Notice that it's still carbon and oxygen and nitrogen, things that are in our body anyways. But the mass is off. Usually carbon is 12. However, this is carbon 11. Usually oxygen is 16. This is oxygen 15. So they're slightly off. Remember, positron is the positive electron. And what happens is, we talked about this before, the positron will then be attracted to a beta particle. And when they come together, they produce a gamma ray. And then those gamma rays are then detected by the computers and create a 3D image. So here's a PET of an Alzheimer's patient. This is a normal brain. Look at the Alzheimer's and you can look at the differences in the redness. For instance, it's like really warm here. Not a whole lot going on there. So you can see the differences between a normal brain and an Alzheimer's brain. Computer tomography is another example. This one uses X-rays. And you can actually see the changes in the depth of the tissue from the absorption. So we're looking at different densities of the brain. MRI actually doesn't use X-ray at all. It's the least invasive imaging method. So it's actually the safest. That's why maybe you hear about it more often, because it's the safer version of it. We have hydrogen atoms throughout our body. They're everywhere. And what happens are, there's a strong magnetic field. And this is a really hard thing to visualize, so I'm going to put on a YouTube video that actually demonstrates it a little bit better with a simulation. But the hydrogen atoms end up aligning. They change shapes. And then because of that, the energy is absorbed when it relaxes again. And the color images are formed that way. But it all has to do with the hydrogen atoms. And here's the MRI scan of heart and lungs. Right, and those are medical ways that nuclear radiation is used in medicine.